In section 3.4, we'll turn our attention to naming ionic compounds, or those compounds composed of a metal and a nonmetal. We don't have much to add in the way of learning outcomes from what the textbook stated, so let's begin. To name an ionic compound, we must indicate the name of the cation and the name of the anion correctly. There are 3 types of cations and 2 types of anions. Each group of ions has its own naming convention that we'll step through one at a time. Only one cation is a polyatomic ion, and that's ammonium. We also have constant charge ions and variable charge ions, each with their own rules. Anions can be monatomic or polyatomic, so keep that concepts to memorize sheet handy. We saw in our last lesson that the alkali metals and alkaline earth metals, plus aluminum, zinc, silver, and cadmium, all have a constant charge. To name these constant charge monatomic ions, we use the name of the element and tack on the word ion, as shown in these 2 examples. When we move into the transition elements, recall that these metals can take on 2 or more different or variable charges. We must note that charge when we're naming them. For these metals with variable charges, we indicate the charge using Roman numerals, such as shown here for the iron 2 and iron 3 ions. If you're not familiar with the Roman numeral system, you'll want to look that up for numbers 1 through 7, which is the highest charge you'll ever see. Here are a few for you to name as practice. Be sure to identify if the metal has a constant or variable charge before you name it. Monatomic anions will have a constant charge. They consist of the nonmetal elements in groups 15 through 17. We indicate they have a charge by replacing the ending on the element's name with the suffix IDE and adding the word ion. This means that phosphorus will become the phosphide ion. Polyatomic anions will contain 1 nonmetal atom and a variable number of oxygen atoms, as noted by changes in the prefixes and suffixes added to the name of the ion. Despite the variable number of oxygens, the charge on the polyatomic ion will remain the same. It's important to be able to recognize these polyatomic ions. Only 2 polyatomic anions end in IDE, hydroxide and cyanide. The others will be distinct because they'll end in ate or ite. Let's take a look at what I mean. If we take this line here with the ATE ending, these are the base forms of the polyatomic ions. If a polyatomic ion can add an oxygen while keeping the same charge and form, we indicate this by adding the prefix per. So chlorate becomes perchlorate, and bromate becomes perbromate. If we go the opposite direction and remove an oxygen while keeping the same charge and form, we trade the ate ending for ite, such as chlorate becoming chlorite. Some polyatomic ions can remove a second oxygen compared to the base form. We indicate this by adding hypo, which means below, to the ite ending. Chlorate, short 2 oxygens, becomes hypochlorite. It's time to put this information together to name some ionic compounds. Keep in mind that the formula of an ionic compound indicates the lowest whole number ratio of cations to anions. This means that there is no need to include ratio information in the name. Rather, you will state the name of the cation, followed by the name of the anion. Let's look at some examples. If you're still building out your naming flowchart for this chapter, you'll want to add this information for ionic compounds. If we consider CaCl2, we see that calcium is a constant charge cation, and chloride is a monatomic anion, which also has a constant charge. We name this compound calcium chloride, dropping the word ion from both names, since they're coming together to form a neutral compound without a charge. FeSO4 is a little more challenging because we see a transition metal, which will have a variable charge, and SO4, which is a polyatomic ion. If you've memorized the charge on the anion, you can quickly identify this as iron 2, followed by the name of the polyatomic ion, sulfate. Here are 3 examples for you to try. This task should be a little easier. Try writing the formulas for the compounds. Hydrates are the last curveball that chemistry can throw us when it comes to naming ionic compounds. Certain compounds, like copper-2 sulfate, will incorporate waters of hydration into their crystalline structure. These hydrates are shown with a dot between the formula unit and waters of hydration, in this case, meaning 5 water molecules are present in the solid for every formula unit of copper-2 sulfate. The blue compound on the left is called copper-2 sulfate pentahydrate. We can also heat the hydrate to drive off the water, forming the anhydrous form, leaving just copper-2 sulfate behind. Try your hand at writing the formulas for these compounds. Use the prefixes we learned in covalent compound naming to indicate the number of waters of hydration present in a compound. As always, I'll leave you with the parting thoughts of the authors.